the next course in the EU Regional School by Steve Lionel. So good morning, Steve Lionel.
Good morning, good afternoon.
Yeah. Steve is giving a course about modern Fortran, so with maybe feature focus on features for high performance computing. But first of all, I would like to give a short introduction why we invited Steve to give a course here. During the preparation of the introduction, I found accidentally this. So it's the TOB index for May 21, and Fortran is back in the top 20. So it's the first time since 10 years that Fortran is back, and people interpret this due to the fact that Fortran is still very attractive for scientists. And yeah, so that's the reason why Fortran is maybe getting more and more popular again. It is a language that is still attractive, especially for people like us working in academia or scientific codes. Maybe Steve will tell us more details about this later, but I found it interesting during the preparation because it's quite recent. So now let me briefly introduce Steve Lionel. Maybe he will introduce himself later as well, but he's well known as Dr. Fortran. Since he is active on Fortran since almost 4 decades, he's a former Fortran compiler developer. And what is quite interesting for the people who are working with Fortran already, he's the head of the ISO Fortran Standard Committee. But why is Steve Lionel so well known? And this is due to the fact that he got 500,000 points in the Intel Developer Zone community. He earned these points from 2000 to 2030 by answering around 20,000 questions. You can compute by your own how much this, how many answers he wrote per day. But yeah, so everybody who's active or who's implementing on Fortran probably know his face from the Intel Developer Zone. So just as an example from our everyday life, so this question was written by a colleague of mine, and I took the wrong answer, but it was answered by Steve a few days later. So it is from 2018, and Sebastian was really happy, and everybody with him to get an answer, a direct answer from Steve. To show that it is not only interesting for PhD candidates, for example, is this discussion Marek had, Professor Baer had with Steve in 2020, also a quite recent discussion. And as more deeply you dig into Fortran, as more important Steve is for you. I would like to stop this introduction by a picture that I found a few years ago in an office of a colleague at ABT. Thank you, Steve. And by asking him for a photo of his board, he wrote me, Steve saved my Fortran C and C++ life. So I think many people working on Fortran can confirm this, and with this I would like to hand over to you, Steve, and we are looking forward to have your presentation, and it's a pleasure for us to have you here.
Okay, let's see here. Okay, I've been answering Fortran questions actually since well, I would say since the late 1970s. When I started with Digital Equipment Corporation, DEC, back in '78, working on the VMS Fortran runtime library. And not only was I a developer, but I was also doing support. I would answer questions about Fortran in the comp.lang.fortran news group. And when DEC introduced its digital visual Fortran in 1997, I started a series of articles that I called Ask Dr. Fortran, which is how all of that started. And most of those are reproduced on my website. I had them on the Intel site for a while, and now I've put them on my own site. The URL is here, and I will make references to that before. It was interesting. I was an Intel alternate to the Fortran Standards Committee since 2008, and went to many standards meetings. And then I retired, and of course I was no longer working for Intel, so I couldn't be on the Standards Committee anymore. But later in 2017, I rejoined on my own, paying for it myself because I have to pay the dues to the US committee and pay for my own travel. And I did that. And then John Reed, who at the time was the head of the international committee, the ISO committee, who had been doing it for almost 20 years, he asked me if I would be willing to take over for the convener role. And foolishly, I said yes. And so then I did that, and then I was reapproved by the ISO executive board for the convener role in 2020. So it's a 3-year position. So I've been doing Fortran a lot, not just Fortran. I spent 5 years on Ada, and I've also done Pascal. But Fortran is where I've done the most. So I'm going to be talking about Fortran. My understanding was, it was explained to me that some of the people on this attending here aren't necessarily familiar with Fortran. Maybe your C++ programmers might. I'm sorry to hear that. But I'm going to talk a bit about, let's see. Oh, come on. Here we go. About the Fortran language, a little bit of history of Fortran, and then I'm going to spend some time going over some of the concepts of Fortran. I'm not trying to teach the language. I couldn't possibly do that. But some of the things I'm going to talk about may not be familiar to you, even if you are an experienced Fortran programmer. I often find that people who have been programming Fortran for many years have not encountered certain aspects of it, or more often that they are not familiar with the newer features of the language. Mostly I'm going to be talking about Fortran as it exists today, Fortran 2018. I'm not going to spend too much time with saying, well, this feature was introduced then and that feature was introduced then. But do keep in mind that you will also be dealing with a lot of existing code that was written possibly decades ago. So I will give little hints about how to deal with that. I'm going to talk about the object-oriented features of Fortran, give some examples there. One of my favorite features of the language is its interoperability with C. Fortran is an unusual language in that it has built into the standard how to call procedures and be called by procedures in other languages, and standardizing this. Then, of course, we get to high performance, parallelization, do concurrent and co-arrays. We spend quite a bit of time on that. Very interesting stuff. And then I'm going to talk about where the standard is going in the future, because we're not standing still. If you have questions during the talk, please ask them in the Zoom chat window. Every once in a while, I'm going to pause and look at the chat window and see what questions were asked. Also, I have this tendency to speak quickly if I'm feeling nervous or don't get the feedback from the audience. So in the reactions button on Zoom, there is a slow down button. And if you think I am talking too fast, please feel free to do that. And I'm hopefully I will see it. We will have a break about halfway through. I'm not exactly sure where it will be, but 3.5 hours is a long time for me to be talking continuously. If there's anything that you think about later that you want to ask about, just send me an email on here, and here's my email address. Or you can go to my blog, stevelionel.com/drfortran, that's Dr. Fortran. And there's a contact me link there. Throughout these slides, I will have a note that says DF : and then it will be a title of one of my many blog posts. I have dozens of blog posts on the Fortran language. And these will sometimes go into great detail about things that I've just mentioned very briefly here. So they're entertaining reads, at least people tell me they're entertaining reads. I try to be entertaining. So just a little bit about how the Fortran language has evolved through the years. Fortran is a very old language. It's one of the first, if not the first, high-level programming languages that came into general use. The original specification from 1954 by John Backus and others, and then in 1956, IBM published this manual about the Fortran language, and it wasn't very big. And then, but that wasn't a standard. It wasn't a standard until 1966, when the American National Standards Institute, or ANSI, published the first Fortran standard called Fortran 66 or Fortran 4, except at the time it was just called Fortran, but we refer to it as Fortran 66. Since then, there have been 6 revisions of the Fortran standard, and the most recent one was Fortran 2018, published in 2018. Now notice that I have here the publication dates in parentheses. The name or the year number of the language didn't match the year of publication. And we decided initially what was eventually Fortran 2018, we were calling it Fortran 2015. And it seemed pretty silly to be publishing in 2018 a standard called Fortran 2015. That would make people think it was already out of date. So we changed the name of it. I will note Fortran 90, notice how long it was between Fortran 77 and Fortran 90. This was originally going to be Fortran 85, and then Fortran 88, and then Fortran 8X, because they didn't know what it was going to be. And then eventually it was Fortran 90. This was an interesting graphic I put together, which is the size of the Fortran standard throughout the years. And as I mentioned earlier, the Fortran 66 standard was pretty small. It's only 39 pages, whereas Fortran 2018 is 539 pages. So you can see that the language has grown a lot, not just in features, which it has added many, many, many features, but also more detailed explanations of things that were largely left to the imagination in earlier standards. I often see people say, oh, Fortran, does anybody still use that? I remember doing it on punch cards and all uppercase, and they're remembering Fortran 66 or maybe Fortran 77. Fortran has evolved a lot since then, and it is a thoroughly modern language. A little bit about how we do the standard. The International Committee is this thing that ends with WG5, that means Working Group 5. It's Joint Technical Committee 1, Subcommittee 22, which is the programming languages, and then Working Group 5 is Fortran. It's made up of experts from national bodies, different countries, including Germany, the United States, Japan, the UK. The International Committee, WG5, sets the goals for what general features are going to be in the next version of the standard. But the actual development of those features is done by the US national body, which is Insights PL 22.3, except that we don't call it that, we just call it J3. And where does that come from? That comes from the old ANSI committee name of X3J3, but we still call it J3. When J3 comes up with a final committee draft, it is submitted to all of the international members for a vote to approve it. And as I mentioned earlier, Fortran 2018 was published in November of 2018. We are working on a new version, a new revision. We're currently calling it Fortran 202X because we don't know exactly which year it will be published. But my hope is it will be published in 2023. And I talk more about that towards the end of this presentation. It's important to understand that the Fortran standard is a little bit different than some of the other programming languages. What it describes is a standard conforming program. And if you have a standard conforming program, meaning that you follow all of the rules in terms of the syntax and the relationship between source statements, then the standard says this is what the program should do. If you deviate from that at all, use non-standard syntax or non-standard relationships, the standard doesn't say what should happen. So that leaves compilers able to add extensions or to add, add meanings to relationships that weren't specified. So an awful lot of programs today use extensions that were very popularly added in the 1960s, 70s, and 80s. When it got into the 1990s, the compiler vendors tended to stop adding new extensions, but they do still exist, and you can still use them. Compilers are required to have the ability to tell you if you use an extension, certain kinds of extensions, numbered syntax rules and numbered constraints in the standard. There are many things that are described in the standard, but the compilers aren't required to check them, and they're certainly not required to complain about them by default, which is understandable because if you want to use extensions, then you don't want the compiler complaining about those all the time. But it is also useful if you have to ask the compiler to tell you what non-standard things you're using, because maybe it's something you didn't mean to use, and that might also impact the portability of your application. The Fortran standard has obsolescent and deleted features. Obsolescent means they're still in the language, but you really shouldn't use them because they are replaced by something newer that's better. And I have an article on that on my blog. Avoid these if you can. I mean, and some of the things are a little bit controversial. Fixed form source, okay, that's a obsolete. Actually, I think that's that's an obsolescent feature. Common and equivalence are obsolescent features. The standard provides better ways of doing those, but you can still use them, and the compilers aren't going to take them away. But you shouldn't use them if in new code. I'm just going to take a brief look at the chat window to see if there are any questions. No questions. Okay. So at the moment. Now I'm going to spend a little bit of time talking about some of the concepts in Fortran, especially helpful if you aren't too familiar with Fortran, but sometimes even if you are. And I apologize if some of this is really familiar to you, but there will be things in here that you may not have known. Get my cursor back. Okay. So, but you know, why Fortran? Why is Fortran still important? And Norbert was talking earlier about the TOEIC ratings of programming languages. I'm not a fan of that particular survey because it uses a really poor way of describing popularity, where it's looking at questions that were posted and GitHub commits. And an awful lot of Fortran is done outside of that environment. It's certainly widely used in the technical and scientific community. And a lot of code, existing code, there's large body of libraries, source code libraries written in Fortran that are used every day. Fortran has array operations. I go into that a little bit more. And when I mentioned earlier about the standard sort of says, you know, what a standard conforming program does, the standard also tries to give compilers the permission to optimize, where they say, well, if you do this, then you're going to get a result that looks like this. And the compiler is free to do things in the way that it thinks is best. For example, in processing an arithmetic expression, if the compiler is allowed to reorder the operations according to the rules of the language and evaluate any mathematically equivalent expression, which may not reference all of the function calls that you have, it may not reference all the variables you have, things like that. Another one is Fortran assumes that there is no aliasing between variables, except when you explicitly say that there can be. Aliasing is where a certain part of memory is accessed by two or more names. Other languages assume that everything is aliased and you have to tell it that it's not aliased. I mentioned earlier, you can mix Fortran with other languages. C interoperability, it's C is sort of the common, the lowest common denominator in many libraries. And Fortran makes it easy to declare routines that can, you can call C from Fortran, and you can call Fortran from C. It has built-in parallel features, two different ways of doing parallelism, and there's a wide body of compilers available from multiple vendors, and there are several open source compilers available, some that are currently being developed, some that have been around for a long time. Freeform source is started in Fortran 90, and this is the way that you should be writing code now. Currently, its source lines may be up to 132 characters long. That's going to change in the next version of the standard. You can have up to 255 continuation lines. That also is going to change in the next version of the standard. Semicolon can end a statement, and you can have multiple statements on a line. Blanks are significant. Please use the .f90 file type if you are using a compiler that in a system that recognizes file types, because the Fortran standard doesn't say how a compiler is to recognize whether a source file is free form source or a fixed form source, which I talk about on the next slide. And I have a Dr. Fortran article on that topic. Okay. And here's the old fixed form source, which was started in the 1950s. You can still use it. You can write for full Fortran 2018 and fixed form source. You should not do this. Blanks are not significant. Here's a funny thing that I have in my Dr. Fortran post that I mentioned in the previous slide. Continuation indicator of a non-blank in column 6, but there's one character, non-blank character, you can put in column 6 that doesn't indicate that it's a continuation, and that's the digit 0. So what sometimes happens is people start numbering their continuation lines. So the first one will be 1, then 2, 3, 4. And if they get to 10, they put a 0 there, and they wonder why they get a syntax error. It's because a 0 in column 6 is treated the same as a blank. Don't use this in new code, but you're probably going to see it in existing code. Fortran program units. Program is the main program. You don't need to have the keyword program. You can just start with your declarations. Fortran has subroutines or functions. Fortran has internal subroutines or functions after the word contains. Fortran 90 added modules where you can have a separate namespace for declarations. And Fortran 2008 added submodules, which I do talk about a little bit later. And then there's block data is the other kind of program unit, and that's obsolete. That's used for initializing common. Identifiers. Alphanumeric has to start with a letter up to 63 characters long in the current version of the standard. It was 6 characters through Fortran 77. It's not case sensitive, so you can have uppercase, lowercase, mixed case, and they're all considered the same. Keywords are also not case sensitive. There are no reserved words in Fortran. Some people got a little bit confused about that, so I wrote an article about reserved words. So if you want to declare a variable named sqrt or do, Fortran doesn't care. Fortran has intrinsic types: integer, real, complex, logical, and character. Each of those types can have different kinds, and those are distinguished by kind numbers. One thing that people get confused about is that the kind numbers, first of all, are specific to any particular implementation. They're not specified by the standard, other than that there is a general ordering from smaller to larger. They're not tied to the storage size, even though most compilers do use a kind number that relates to the storage size. Complex is a little bit unusual in that when you say complex, kind equals 4, you mean a complex that consists of 2 real kind equals 4 values. There is an extension that many people think is part of the standard where you say real *4 or complex *8. Those are extensions. Don't use them in new code. There are intrinsics, these selected intrinsics that you can use to ask which kind has these qualities for precision, range, or for implementations that support multiple character sets, which character set you want. Character types might have fixed length, except the new in Fortran 2003 deferred length allocatable. And again, I have a Dr. Fortran post on kinds. Fortran has derived types, which are user-defined types, And the syntax for this starts with the keyword type in your type name, then a list of things it contains, and then end type. And the components, they can be intrinsic types, it can be derived types. When you're referencing a derived type, you use % to separate the components. You will see lots of uses of a dot, a period, for a separator. That's the old DEC extension from the 1980s, before Fortran 90 came out with derived types. I think in 1985, DEC created a structure record extension and used dot as the separator. At the time, we thought that we knew this was not going to be what the standard ended up with. And we didn't think there was going to be a ambiguity with whatever the Fortran standard had. We did not count on the fact that user-defined operators look like component references. So if you have A.B.C, .B. could be an operator that the user defined. And so the compilers that support this extension have to be able to disambiguate, decide what do they mean, a component or an operator. The Fortran standard does not have unions. And it's a bit tricky to do union type things in Fortran, but it can be done. But there's no unions in Fortran. Constants can have an optional kind that's specified by an underscore followed by the kind indicator. Afterwards, the kind specifier can be just a number, but it'd be better to use a named constant or a parameter constant, like I show here with underscore DP. Fortran has array constructors. You can use square brackets. There's also an older syntax, left parenthesis slash the values and followed by slash right parenthesis, that has been, we recommend using the square bracket syntax instead. If you have a derived type, you can have a constructor for those. You give the type name and then a parenthesis and then the components. You can use the component names if you want. So you can say my type, left parenthesis, A equals 3, comma, B equals ABC, quote ABC, whatever, if you want. The exponentiation operator is 2 stars. It's not the up caret. There are comparison operators. Originally, Fortran had operators such as .lt. Fortran now has the symbol operators that are more familiar to in other languages. There are these logical operators. And again, I have a Dr. Fortran post that talks about where logicals and numerics really shouldn't mix, even though some compilers allow them. And you can create your own operator, such as dot product dot. I have a Dr. Fortran post on expressions, constants, and operators. That was, I think I published this one just last month. Fortran is an array-oriented language. Arrays are where Fortran's real strength is, and there are many different kinds of arrays. Some of these may be familiar to, and some of them may not. The first 3 have been in the language since Fortran 77. Obviously, the first one, explicit shape, where you just give the size of the array. That's pretty obvious. Adjustable arrays are where the array dimension comes from a dummy argument or a common block, or in newer Fortrans, a module variable. Traditionally, this was only allowed in a dummy argument list and a procedure argument list, but Fortran 90 allows you to declare a local variable whose dimension is not known until runtime based on some other variable. Those are called automatic arrays. Assume size is not something you should be using anymore. This is an array where you don't specify what the upper bound is, and the compiler has no idea what the upper bound is. So it's your responsibility, the programmer's responsibility, to ensure that all array references remain in bounds. Assume shape arrays are for dummy arguments where the shape is passed in by the caller. Deferred shape arrays have the same syntax, but this is where the variable is an allocatable or a pointer variable. And deferred means the shape is defined later when the variable is allocated or pointer assigned. One that you may not be aware of, called implied shape, is used when declaring named constants or parameter constants. Okay, I'm noticing there are things in chat, so I'm going to stop at the end of this slide and look at the chat window. And this is where you say, use an asterisk for the dimension, and it's taken, the actual shape is taken from the constant you initialize the parameter constant to. And then there's the relatively new in Fortran 2018 assumed rank, x paren dot dot, where x is a dummy argument. And I talk about that when I go into C interoperability. In the current Fortran standard, there's a maximum of 15 dimensions, but of course, compilers are free to support more of those. And although the default lower bound is 1, you can change that if you want. So let's see, what are people asking in chat? Okay, are capitalized suffixes F and F90 the pre-processing part of the standard or just custom? Okay, the Fortran standard does not talk about how source lines get fed to the compiler. The way I joke about it is, it's as if fairies deliver them in the night. The Fortran standard does not talk about what source file name looks like, which is why I recommend you use .f90 lowercase for Fortran source files. There is a convention on some platforms, mainly the Unix and Linux type platforms, where a capital F or a capital F90 means run the preprocessor before the source, but that's certainly not part of the standard, and preprocessor is not part of the standard. So it is just custom. I'll note that on Windows, where file names are case preserving but case insensitive, those suffixes don't tend to mean anything. Well, it depends on the implementation. I know that Intel Fortran does not treat capital F and lowercase f any different. Okay, I said that I talked about reserved words. Why would Fortran allow this? Well, reserved words actually cause problems for programmers, and it really doesn't cause a headache for the parser. The way Fortran statements are parsed, I've written Fortran parsers. It's context matters, and there aren't any cases in the language where it would be ambiguous. The only rule that Fortran has that even comes close to a reserved word is that you cannot have a statement that starts with the letters END that isn't an end statement. And all the so you can't have you can have a variable named END, but you can't do something like END and then continue that onto the next line and assign to it. You can put it all, you can say END equals 3 if you want, that's fine, but it can't look like an end statement in the first line. Other than that, you can call things whatever you want. it's a language design. It doesn't really cause headaches for the parser, and it doesn't, what it means is that the language can introduce new keywords without breaking people's programs that happen to have declared variables with certain names. Now, there is an issue with intrinsic functions. Fortran has added intrinsic functions, many intrinsic functions over the years. If you are using your own function that matches the name of an intrinsic function, if you've properly declared it, then the compiler will say, okay, I know they mean the user's function and not the intrinsic function. Or you can use the intrinsic statement to say, yes, here I mean the intrinsic function and not the user's function named squirt. Okay, next. Type-specific intrinsics, like, okay, these are, yes, specific intrinsics, like DABS or DSQRT seem to have been dropped. Well, it's not that they've been dropped, but we haven't. Okay, Fortran has generic intrinsic. SQRT is a generic intrinsic. In the early Fortrans, there were no generic intrinsics. If you wanted a double precision square root, you had to write DSQRT. Then Fortran added generic intrinsics where SQRT, and then it took its type from the type of the argument. Since I think Fortran 95, I believe, no new specific intrinsics have been added. There is still a table of them. You should not use them. You should use the generics if possible, because one, we're not adding new specifics, and they don't add any value, except for the odd case of passing an intrinsic as an actual argument to another subroutine. People don't do this very much, but that's the one place where the specific intrinsic can be used. But I think that that's a very rare case, and you should just use the generics where you can. And that can also take it, especially if you're writing your own generic interfaces, which I don't talk about today, because I'm not trying to teach you the entire language. You can have your specifics and then your generics and use whichever ones you want. Norbert says, did I understand correctly that types like real star 8 are extensions that should be not be used? Yes, you did understand correctly. That is an extension. It is a non-standard syntax. It is extremely common. Of course, prior to Fortran 90, that was the only way that you could, well, I mean, you could say double precision for real star 8, but more interestingly for integer types, if you had an implementation where you had 2-byte integers or 4-byte integers or 8-byte integers, you needed some way to be able to say that. So the compiler writer said, okay, put in integer star 2, integer star 4, etc. The Fortran standard in Fortran 90 didn't go that way, and they used the kind numbers. So these star n for variable sizes are not are extensions, and you should not use them in new code. I'm not going to complain a lot if you use them, especially if you're used to it, but I would encourage you to use the standard syntax. So, okay, that's all the questions for now. Please do ask questions later, and I will get to them. Okay, control flow. Many different kinds of control flow in Fortran. The do loop has many different kinds. There's the original counted do loop where do I equals 1 to 10. An interesting thing about counted do loops that people don't understand is that the count is determined at the beginning of the loop, before the loop starts executing. So if I say do I equals 1 to 10, 1 comma 10, the compiler will compute the number of iterations, and then it will execute that number of iterations, even if the loop control variable changes in the middle, which you actually are not allowed to do by the standard, but some compilers will allow it, or if one of the upper bound, the end of the loop, is a variable and you change that value, that doesn't change the number of iterations. There is a tested do, pre-tested do, the testing at the top of the loop. There is no bottom tested do version, but although you can implement that with exit, which I mentioned before. There's an infinite do, which simply do until you somehow terminate it another way. I do mention exit. Exit exits the current loop, or if you have a labeled loop, and by label I mean the label colon, as I show in the first line there, it exits that loop. There's a parallel allowed do, and I'll talk more about this later. It's called do concurrent, that was added in Fortran 2008, 2003, I think 2003, 2008, I forget, but I talk more about that later. The cycle statement will skip to the next iteration of the loop. You will encounter obsolete and deleted forms of do. Do with a numbered label 10, like do 10 I equals 1 comma 10, and then later a 10 continue. That's considered obsolete. And then there's a do loop where it ends on a statement that's not continued. That's just an ordinary executable statement. And that's a deleted form. Don't use that either. It's very confusing as to which loop that end statement is part of. And I have an article that I wrote way back I think in the 1990s called About Obsolescent and Deleted Features. I'm not a fan of deleted features because even though the compilers are going to continue to support deleted features because people are using them, when a feature is deleted, it's simply removed from the standard. And that means that there's no text telling the user or the compiler writer how that feature should interact with the rest of the standard. At least obsolescent features, which are printed in the standard in a smaller font, there is text that says how they should work with the other features. Every time I ask the other compiler writers on the standards committee, do you ever intend to remove deleted features from your compiler? The answer is no. One, people are still using them. And two, it's actually more work to remove the feature from this compiler. And anytime you make a change, as you're all programmers, you know that the number of bugs you introduce is the square of the number of lines you change. So try not to do that. There's various forms of if. You can have a single line if, where you can simply say if expression, then one statement, or you can say if, then else. One thing that you need to understand about ifs is that your expression, there is no short circuit evaluation and no strict left to right evaluation of logical expressions. The compiler is allowed to evaluate any logically equivalent expression to any degree of completeness. There have been proposals to add short circuiting such as a dot and then or a dot or else, but they failed to gather enough support. So you need to use if then else to separate things. There are several kinds of selects. Select case is sort of the equivalent of the switch statement in C that can be used on multiple data types. In a select case, case default is where it doesn't match any of the previous cases. And in this little example here, I use the error stop command statement that stops the program. Fortran 90 introduced modules, which I remember from my Ada days, and these are separately compiled declarations and or procedures. So here is an example, and to use a module, you use the use statement and name the module. If you don't do that, then those definitions are not available to you. And the nice thing about modules is that you can have many modules. You can also restrict which things from the module are to be imported. There are, you can rename them if there's something that collides with a name that you're using. It's very flexible. Fortran 2008 introduced submodules, which is an ability to have your interface declared in the module and the implementation in the submodule, so that you can recompile the implementation, thus you fix a bug without causing all of the sources that call that routine to be recompiled. That's assuming that you didn't change the interface to the routine. And I have a post on that one too. If you've been programming in Fortran for a long time, you know that you can simply call a function or a subroutine without declaring it, as long as, well, we'll get to this in a moment. So before Fortran 90, all procedures were implicit, which meant that the only thing that you could possibly know about a procedure was a function and what data type its function was. In the very early, very early Fortrans, there was, I think, well, it's really not relevant, but the initial letter, the implicit types, I through N are integers and everything else is a real. But you could declare what the type of a function was, but you couldn't declare anything about the arguments. And you couldn't do things such as this function returns an array. So Fortran 90 introduced explicit interfaces where you declare all of the characteristics of the procedure. If you put a procedure in a module, or you have a contained or internal procedure, that explicit interface is automatically created. You don't have to do anything else. You can write your own explicit interface with the interface block. Certain kinds of dummy arguments and function results require you to have an explicit interface to be visible. For example, if you have a function that returns an array, if you have a procedure that takes an assumed shape dummy argument, requires an explicit interface to be visible. There is in Fortran 2018 a new feature called implicit none parenthesis external. If you say that, it forces you to declare all the procedures you're using, so there would be no implicit interface. And I have I actually have 2 Dr. Fortran posts on explicit interfaces. Fortran has dynamic allocation. Pointer was the first thing, and C programmers get a little bit confused by this because a pointer in Fortran is not just an address like it is in C. It also contains shape information, and when you get into object-oriented programming with polymorphism, it contains the dynamic type information. There is no explicit dereferencing of a pointer. If you simply use the pointer name in an expression, that is the reference to the data. There is a separate pointer assignment syntax where you are assigning the pointer to whatever the target of the right-hand side is. I mentioned earlier that there's no aliasing in Fortran. Fortran has the target attribute that tells the compiler something, there might be aliasing of this thing. Anything that that's declared as a pointer is automatically a target. You can only pointer assign to something that has the target attribute. Pointers can be discontiguous. They can have a stride other than one. You are responsible for avoiding leaks of pointers. There's no garbage collection. There's no automatic deallocation. There's no reference counts. It's your responsibility to do that. Allocatable is a little bit different, where it is basically a dynamically allocated variable where the shape, and by shape I mean extent, the number of elements in each dimension. You always have to declare how many dimensions, the rank of an array when you declare it. Allocatable or anything else. I'll talk about assumed rank later. It's a little bit weird. Allocatable arrays are always contiguous, and there's no aliasing between allocatable arrays, unless of course you put target on it. One of the interesting things is that if you have a local array that's allocatable, so you come into a procedure and you allocate a local variable, local allocatable array, that will automatically get deallocated by the compiler on exit to the routine. So there's no leaks, assuming that there's no bugs in the compiler. If you do an intrinsic assignment, if you say A equals B, where A and B are allocatable arrays, and there are different shapes, the Fortran will automatically reallocate the left side to match the shape of the right side. There is also now deferred length allocatable character strings, which is sort of like varying length strings. And you can assign to them and they will automatically get allocated to the appropriate length. Input, output. Fortran was generally record-oriented. Fortran 2003 added stream access, which is more C-like, which is just a sequence of bytes. Fortran does have both formatted and unformatted I/O in all of its access types. Unformatted stream I/O is just that, a sequence of bytes. Formatted stream I/O has record separators, record terminators that vary by platform. For example, on Windows and Linux, they're different. A question that C programmers often have when they move to Fortran is, how do I do the equivalent of sprintf? Or how do I read from a character string, convert a character string to binary? And that's done with internal I/O. Okay, I have a question in the chat window. Okay, very good. Not a question. All right, let's see. So we've been going for an hour, but I'm going to continue for a few more minutes, for a little bit. no question. Well, first of all, are there questions about anything I've said so far? No, I'm not seeing. Okay, nobody's got questions. I hope I haven't bored you yet. We're going to start getting into some fun stuff. Fun, Fortran, yes. Okay. Fortran 2003 brought object-oriented coding into the Fortran standard. You can extend a type by extending an existing derived type. Pretty much every derived type can be extended. There are a couple of exceptions that you can look up in the standard or in a language reference manual, but it's not too important. In Fortran, the type that's extended is called the parent type, and an extended type has all of the components of its parent plus its own components, and the parent type itself is a component of the extended type. I have a post on this called Not My Type. And here's an example where we declare a type parent, which has one component, P1. Now we extend that type to be a new type called child, and it has an additional component, C2. And then we declare a type, a variable of type child, which is the extended type called kid. And there are obviously kid C2, %C2, that's the one component. It also has the P1 component from the parent, and it has a component that is the name of the parent type, kid %parent. And then you have kid %parent %P1. You can reference that too. A polymorphic variable is a variable that has a declared type, which is what you specified when you declared it, and the dynamic type, which is its runtime type. That's polymorphic variables are declared using the class keyword, where you say class parenthesis and then the name of the declared type. So it can have an object. It can be a thing of the declared type or any of the extensions of the declared type. Doesn't just have to be a pointer. It can be a variable or a dummy argument, but pointers are sometimes more useful here. Also allocatable, and when you allocate an allocatable polymorphic, you can specify what the dynamic type should be. So even if P was declared with a declared type of parent, we can declare it with allocate it with a, well, this can also be a pointer, can be allocated with a dynamic type of child. A polymorphic variable is type compatible, which means you can sort of go from one to the other with an object of the same declared type or any of its extensions. And I talk about this in the Not My Type post. It's a little bit confusing. You can pass, for example, a larger type to a smaller type. So I could pass a child to a parent, but the called procedure could only reference the components that it knows about in the declared type, which is parent. You cannot pass a thing declared as parent or dynamic type of parent to something whose declared type is child, because then it could be referencing components that don't exist. There is unlimited polymorphic declared as class paren star paren, and everything is type compatible with that. You can pass anything to an unlimited polymorphic, but you can't do anything with it unless you know what type it is. And therefore, the Fortran language has the select type construct to query the unlimited polymorphic thing to say, okay, really, what type are you? And then it can do something with it. So I see some questions in the chat window. Okay. The parent type is itself I wrote that the parent is itself a component of the extended type. Is it true that it's only accessible in the case that the parent is non-abstract? That's an interesting question. I don't know the answer to that offhand. I'd have to look it up. I will do so during the break later and get back to you. Circle back to you, as somebody in the US has been frequently saying. But I will remember that. Good question. You can declare type-bound procedures that are referenced in the procedure. So here I have a module with a type point, and I say it contains a procedure called radius with a specific procedure, point radius, and comma pass is the default, which passes the thing that I'm referencing as the this argument. Of course, if you're a C++ programmer, you recognize this. And now I have the point radius function that declares this argument as class point, and it's important that it be class and not type. Intent in, by the way, intent, I don't talk about that in this presentation much, but intent is a declaration to the compiler of what you're going to do to the dummy argument. In means you're only going to read it. Out means it's initially undefined on entry to the routine, but you're going to define it. In out means it may be read or written, may be, not required to. And if you don't have an intent at all, that means that you're not saying what's happening to it, and the compiler has to assume the worst. So in this function, we call the squirt function with arguments of the fields from this. And now in the program, I call the function by saying p% radius. P is the variable of type point. Now radius is essentially a method for that type. And I don't have to specify any arguments to it because P is implicitly passed as the this argument. Chat question. What does a equal sign greater than mean? That is a pointer assignment statement that says A, which is a pointer, points to B, whatever B happens to be. If B can be a variable with a target attribute, or B can be another pointer, in which case it means it points to the target of B. And in pointer assignment, you can also specify bounds for a pointer array, and you can change the bounds of a pointer array called pointer bounds remapping. That's a fairly new feature in the language. Another question. Excuse me. Oh, yes, you're right. You're right. Okay, I think he's asking about the renaming of the type-bound procedure. Yes, I missed where that was. Here in the procedure statement, I could just say point radius for the name of the procedure, but here I'm going to say radius is the name that's to be used when referencing this, and it's using point radius as the implementation for the radius function. Fortran will use this syntax, this equals greater than syntax, in various places to indicate a renaming of things. It's also used in the use statement if you want to rename something. It's used in The associate block, which I don't think I talk about today. But yes, that's what it means here. Is point radius is the actual internal name, and radius is the name that it's used, is the method that's used. You can override procedures. For example, I might extend type point, and I might have another function that I call radius that overrides this one, and there I would essentially point to or rename it as a different internal routine. I don't have an example of that. Okay, C interoperability. It's one of my favorite features of language. And it opens a lot of opportunity to take advantage of existing libraries that were written to be called from C, or that were written in C. In the past, Fortran was very commonly mixed with C, but you needed to use various vendor extensions to do that. For example, if you wanted to use mixed case routine names, there was no standard Fortran way of doing that. If you wanted to pass something by value, there was no standard way of doing that. If you wanted to pass a character string, different Fortran implementations would pass the length in different ways. There might be a length at the end of the argument list. There might be a length right after the address of the character string, or there might be an address of a descriptor. Back when I was doing VMS, that's the way we did it there. And sometimes this was documented and sometimes not. If you were writing C code to be called from Fortran, you had to use conditionals to say, well, if I'm using compiler X, then I have to do it this way. If I'm using compiler Y, I do it that way. Some compilers in some platforms add underscores to the ends of Fortran procedure names. Some upcase them, some downcase them. Everything was non-standard there. So Fortran 2003 added C interoperability, where you could say those things in the standard language and be able to reference a lot of things that were callable from C. Now, this is C and not C++. You can call C++ as long as you make it look like C. Typically in the your C++ code, you say extern quote C quote to prevent name mangling and some other things that C++ would do. So Fortran has some standard syntax for enabling data to be procedures to be called and data to be passed between Fortran and C in both directions. There's a module called ISO under C under binding that declares, I think I'll talk about this in the next slide, but there's definitions and restrictions to make sure that your Fortran code and your C code are talking about the same thing. Now, the Fortran standard talks about a companion C processor. So each Fortran compiler identifies in its documentation which C compilers or compilers are its companion C processor. Let's say for Intel Fortran on Windows, that would be Microsoft Visual C. On Linux, it would be GCC. Now, that doesn't mean necessarily that you have to use that exact compiler. And in fact, it doesn't mean you have to use a C compiler at all. It's just that it uses the assumptions that are made by that C compiler. And this handles procedure naming, data types, layout of derived types, and how arguments are passed. I wrote an article called I Can See Clearly Now. I called it Part 1. Many years ago, I always had meant to write a part 2. I never did, but I might still get around to it. the Fortran standard gives mappings between different Fortran intrinsic types and how it should look in C. So there's this module ISO under C under binding that defines a bunch of parameter constants for various C kinds. So you would say something like integer parenthesis C under int, right, parenthesis, to get a Fortran integer that is the same as the companion C processor's int. And there are many, many of these. If there is no corresponding Fortran kind to a particular C type, then the definition in ISO C binding will be -1, which will then get you a compiler error when you try to use it. You can declare a derived type with the bind C attribute. This is a special syntax to say, I am interoperable. You can put that on derived types. You can put that on module variables. You can put that on common blocks and on procedures. For a derived type, all the components must be interoperable. They must be one of the types that Fortran supports as being interoperable with C. You're not allowed to have any pointer, allocatable, or co-array components. And very important, the layout in memory for your Fortran derived type will then match that of what the C compiler would do. And that includes adding any padding that the C compiler would do. And it also prevents Fortran from rearranging the components as it otherwise is allowed to do. See, I have a question. Would it be possible to call a C++ template function? No. No, you cannot call anything that's not extern quote C quote. There's no support for that. Okay, it seems that the Intel Fortran you mentioned is a strong mix between Fortran and C. We have sometimes had very big problems making code developed on Intel platforms readable for other compilers. Do I expect Intel to move farther away from the standard in the future? And what advantages do you see in using the Intel standard? I don't understand the question because the premise seems wrong to me. Intel Fortran has stuck to the standard very closely, and it implements the full range of C interoperability features. I don't understand what Norbert, what you meant by strong mix between Fortran and C. Norbert, could you perhaps unmute and tell me more about what you meant there?
So my impression, so I don't have an example anymore in mind anymore, but in the past there were some C extensions available for, I think also in type declaration, that were not readable by GNU compilers, for example. Unfortunately, I don't have an example anymore in mind, but in my opinion, by implementing or developing using the GNU compiler ensures that your code is readable with other compilers like Intel, but if you do it the other way around, then you can run into problems. And but if you say that Intel sticks with the standard more or less, it might be the case that Intel introduced already parts from newer standards before the GNU compiler, before the these extensions or new structures were introduced to the GNU compiler. But
sure. Okay, there's two parts of that. Yeah. First of all, Intel has not added any C features to derived types of structures. What you might have encountered are DEC Fortran extensions, structure, record, things that start with %sign. Those all came from DEC Fortran, VAX Fortran. And those were still commonly used, and you might see, well, yeah, some %fill, I think, is one that came from DEC Fortran. I'm not aware of anything from C that Intel added to its Fortran compiler. There are a couple of intrinsics, like malloc and free were added as intrinsics, but that, intrinsics can be added anywhere. It is absolutely true that Intel was farther along than G-Fortran in implementing the Fortran 2018 C interoperability things, which I do talk about a little bit later. G-Fortran has caught up partly. I know they weren't doing any of the Fortran 2018 C descriptor things for a long time. And they don't implement everything, and maybe not everything is implemented correctly. But absolutely, Intel has not added a syntax extension to its Fortran implementation. In all of the time I was with Intel, I don't think we added any actual syntax. We added directives. I mean, everybody's, directives for helping the compiler, things that start with that look like a comment. But no, not adding. Intel did not add anything from C. But you would find things such as many DEC extensions in people's code that other compilers might not understand, or you might need to use an option on the other compiler to have it understand those things. They're usually referred to as VAX extensions because that's where they came from. But absolutely use the standard wherever possible. I've always said that for maximum portability. And as I think I did say earlier, every once in a while, turn on standards checking and see what the compiler warns you about, because there might be something you're using that you did not intend to be non-standard. Okay, so I will continue. 23, so hour and a half. Okay, Fortran 2018 included something that was called a technical spec, TS29113, that was actually approved in 2012, that extended C interoperability past what Fortran 2008 had. And it now allows additional kinds of dummy arguments to be passed between Fortran and C, including assumed shape arrays, assumed size arrays, character variables with character values with length other than 1, and allocatable or pointer variables. And the way all of these are done are with a new structure that's called a C descriptor. Now, this is a Fortran construct that is used in C code to understand what Fortran passed to it. A C descriptor is a struct that's defined by an include file. I'll talk about this in a moment. And it has an attribute code. So it says, is this a pointer? Is this an allocatable, or is it something else? What the data type is, the base address, how long each element is, how many dimensions it is, and what the, if it's an array, what the bounds and extents are for each dimension. When Fortran calls a C routine and you are passing in, you have in the dummy argument one of these types of things that were not allowed in Fortran 2008, such as an assumed shape array. the Fortran compiler creates and passes a C descriptor to the C routine. The C code can read this C descriptor. There are these functions called CFI underscore something that are provided by the Fortran compiler in a library that the C code can link to, that will help understand and create these descriptors, read these descriptors, modify the descriptors. C code can create its own C descriptors, pass them to Fortran. The Fortran procedure must have the bind C attribute in order to recognize these. Fortran code never sees a C descriptor directly. Your source doesn't know that they exist. It's all handled implicitly by the Fortran compiler. Back up one. Each Fortran compiler provides an include file, a header file called ISO under Fortran under binding.h, and the case is mixed just like this, that describes the layout of the C descriptor and declares prototypes for all of the CFI functions. One thing that you need to be careful about is character paren star dummy arguments, which are basically past length character arguments. In Fortran 2003 and 2008, you could not pass one of these. You could not have a interoperable routine declared with one of these dummy arguments. You could pass a character variable, but you had to declare it as an array of single characters. You can now have a interoperable procedure that's declared with a character paren star paren dummy argument, but then the Fortran compiler will create a C descriptor for it. And if the called C routine is not expecting a C descriptor, it's not going to work. Now here's an example. This is the C code example, part of the example. So here we include the ISO Fortran binding.h header file, declare a Fortran routine called greetings. Notice this is a C++ code, so it's I have extern quote C quote. If I just said extern in Fortran in C, it would be fine. And it takes as a dummy argument a C descriptor. This is the way we declare it in C. CFI under CDesc T, that's the type of a C descriptor, passed by reference, by pointer. The main program declares its own C descriptor. This is with an uppercase CFI under CDesc under T, and the paren 0 means it's rank 0, so it's a scalar. So that basically creates the space for it. Calls CFI under establish. This takes the our local C descriptor and fills it in with the appropriate values as the corresponding Fortran implementation wants. Now, this is going to be an allocatable variable that's of type character. As allocatable, it's deferred length. We allocate the string, and don't use malloc here. You have to use CFI under allocate. So this is an allocate that the Fortran understands. And now we've allocated it to length 7. We copy in the string hello, comma, space. And now we call the Fortran routine and pass it this C descriptor. And if I go to the next, after we get back to the call, we then print the length of the string, and then we deallocate it. You don't use free, you use the CFI deallocate. Always use the CFI routines to allocate and deallocate things that Fortran believes are pointers or allocatables. And so here's the Fortran routine. Notice that there's no C descriptor here. It's just a string argument. We have bind C that says this is an interoperable Fortran routine. We declare the dummy argument to be character assumed length, past length, assumed length allocatable, deferred length allocatable, excuse me, get the right words here, Steve. And then we simply use it. And we assign to it a concatenation of the original string followed by the word world with an exclamation point. And now we print it. And notice that it has the value that C put in it, concatenated with world. We return, we print the length is now, and then we print the length is, it's now 13. So we get back, when we get back to C, it's already 13 characters. And then C deallocated it by the call to CFI or deallocate. The additional C interoperability features in Fortran 2008 were largely driven by MPI, which wanted to make it easier to call MPI routines from Fortran. So one of the things was that in MPI, you might have a buffer of some arbitrary type that you wanted to pass. And there was no easy way to say that in Fortran because Fortran was strongly typed. So Fortran 2018 adds assumed type, which is declared with type paren star paren. And this is sort of like void. It has no declared type. It can only be used for dummy arguments. And there's not an awful lot you can do with it in Fortran code. The only way you would possibly be able to manage this and reference it in Fortran code is first get a C pointer to it using the CLock intrinsic function, and then use the intrinsic function C under F under pointer, is actually module intrinsic function, to cast that to a Fortran pointer, and now you can use it. But it's really intended for calling an external routine where you don't know what the type is, or you don't care what the type is. And when it's coming into Fortran, there's no type information, so you can't do anything with it directly. If you have an interoperable procedure that has an allocatable intent out argument, remember earlier I talked about allocatables have no memory leaks. So in a normal Fortran routine, if you have an allocatable intent out dummy argument and it's allocated when it comes into the routine, Fortran creates code to automatically deallocate it before the routine starts. It was decided that we could not assume that C procedures were going to do the deallocation. So if you call a interoperable C routine and pass it an allocatable, and that dummy argument is declared with as allocatable intent out, the calling routine will deallocate it first before it gets to the C routine. And so that means possibly that if you have a interoperable routine written in Fortran that has bind C and you call it from Fortran, the check for allocation will happen twice. It won't deallocate it twice, but it'll look twice. Fortran 2003 added a contiguous, maybe it was 2008. I lose track of when different things got added, but there was a contiguous attribute that helps with optimization, to say that a particular dummy argument is contiguous, that it doesn't have a non-unit stride. And if when a routine comes in, when you call when you call a routine where the dummy argument is declared as contiguous and you're passing a non-contiguous thing, normally the called routine will check to see whether it's contiguous and will make a copy of it. We'll do copy in, copy out. That will happen. Yeah, excuse me. That happens on the call. The caller does the copy in, copy out. But an interoperable routine in Fortran that has a contiguous dummy argument, it has to be able to handle a C descriptor that describes a non-contiguous array. Interoperable procedures may now have optional dummy arguments that are represented with a 0 or null address as in the argument list. And there was quite a bit of argument about this in the standards committee, whether that would be allowed, because there was an implementation that this would be incompatible with, but it went ahead and was approved. There was an asynchronous attribute for something called asynchronous IO that I haven't talked about today. But this was extended to variables, again for MPI, to say this variable might be read or written after the call returns. So if you're doing an MPI code and you say an MPI send and or MPI receive, and then you do an MPI wait, this tells the Fortran compiler that that variable might not actually be live until sometime later, and therefore not to assume that it can make a copy of it into a register or something like that. Assumed rank is another thing that was added for MPI, although you can use it in your own code. And if you were writing a Fortran routine that could accept an array of different ranks, you had to write a different one, a different interface, or actually a different routine for each rank. And this was bad enough if you had one array argument that could be up to 15 dimensions or more in some implementations. But if you had 2 or 3 arrays that could be different ranks, you would multiply the number of possibilities. So now there is a declaration of a dummy argument, dimension paren dot dot. You can sort of think of it as a colon on its side. Here the rank is passed somehow. If it's an interoperable routine, it's passed by C descriptor, but it doesn't have to be interoperable. You can use this in a non-interoperable Fortran procedure. There is a new select rank construct to say, okay, this thing came in, what rank is it? And within the in each individual case, you can now reference it as if it was that rank. So there's a choice of rank n, where n is 1, 2, 3, 4, or 0. Rank 0 is scalar. Rank asterisk means it's an assumed size array that was passed in. And rank default means I don't know what it is. It's something else. It didn't match any of the existing cases. Okay, I've been going for an hour and a half, hour and 40 minutes, and I think it's time for a, let's take a 15-minute break. I need to rest my voice for a bit, but if there are questions, and please ask them in the chat. I'm going to pause sharing for a bit. I get this right. And I'll leave the chat window open. So what we're going to do is get out of this. Okay, some interesting questions came up. Let's see, I'm not muted. Okay. Interesting questions came up during the break. Okay. So Thomas had asked about when I was referring to the parent component and a question about non-abstract parent types. Well, you can't have, an abstract component can't be the rightmost thing in a data reference. And the thing is that abstract, unless, and there's some rules about polymorphism. I think I probably would need to have take a bit more time understanding the question, but generally an abstract type is a type that's not going to have its own, you can't declare anything specifically of the abstract type. So you can't have a parent component that's of the abstract type. You can only reference an extension of the abstract type. Back here. Okay. Paul was asking about something that works in iFort and not G-Fortran. Well, there are something with associate with B associates to A and then C associates to B. I don't think you're allowed to do that, although I was just looking at the standard and I couldn't yet identify the wording that that allows that. Oh yes, Cray pointers. Yes, that's Cray pointers are a long time extension. Yeah, those are supported by many compilers. The GNU compiler took a long time to add some extensions. I mean, this is an interesting thing. There have been attempts over the years to implement Fortran compilers that are strict to the standard. And I say, okay, well, we should just implement what's on the standard. And in fact, there were two compilers in the 1990s, one that was called F and one was called ELF, ELF, Essential Language Fortran or something like that, which were not only just the standard, but they were actually portions of the standard that the authors thought that the users should stick to. Nobody used them. That was just the reality. The reality in the Fortran world is people use the standard, and at least in the past, they were using all of the standard and they were using extensions to the standard. Back when I worked for DEC and Intel, we certainly had customers who warned us that we had better not start automatically giving warnings or even dropping support for non-standard features. Leave warnings by default because their applications depended on them and they weren't about to rewrite them. That's fine. I'm not in favor of rewriting a working application. Just try not to use extensions in your new code. Cray pointers, yeah, you can pretty much everything that you could do previously with Cray pointers, you can do now with Fortran standard support. It may be a little clunky. It may be a bit complicated, difficult, but it can be done. And I think works better with the type safety of Fortran pointers over the non-safe Cray pointers. Okay, Thomas has another question. Is there a clean way of having two types A and B defined in two different modules that point to each other? A points to B and B points to A, sort of circular point. You can actually do this with submodules. It's not really, the problem is that you don't necessarily have the type one of the things defined when you declare the other ones. I think there's a way to do this with sibling submodules, but I'd have to go look again and do it. I've seen examples of it. But I would say that that's bad code design. Okay, Norbert. In the past, most compilers already perform type checking, but through a warning instead of errors. Compilers now change the strategy. Sometimes leads to conflicts. Oh yes, absolutely. You know, that's especially when you use MPI. Okay, and this is entirely why the extended CON interoperability things were put into Fortran. So you could have things like assumed rank, and you can have type star, where you are telling the compiler, I will be passing things of different ranks or of different types here. Don't complain, and allow the called MPI code to check that. MPI has, I think they call it MPI, I don't know if they call it MPI F08 or something like that, that actually uses these new features. And if you use that module, then you can use, you can bypass the type checking because it uses type star and assumed rank. That would be my recommendation for how to deal with these conflicts. I am all in favor of compilers complaining when things don't match. As a longtime support person, because I did both development and support many times at the same time, I kept running into user code that had errors in terms of violating rules of the standard. The compiler didn't check by default, and they complained when the program broke. And that's because they weren't aware that they had made an error, especially type mismatches. So don't disable the type check. Use the standard features for telling the compiler that things can be of different types. Okay, let's see. We're gonna get back to the slides now. I'm going to talk about the parallelization features of Fortran, sort of parallelization. The first thing that Fortran added back in Fortran 95 was something called for all. And this came from a dialect of Fortran called high performance Fortran that DEC actually implemented in its DEC Fortran 90, and as did a couple of other Fortrans, but it never went anywhere. People weren't using it and it faded away. And for all was intended to allow a compiler to parallelize a loop or a block of code. And it was a series of array assignments that could be done in any order to any degree of parallelization. Unfortunately, the way for all was specified, give me just one moment. I forgot to close the door. Otherwise, I might have had a cat coming in to help out. Was that each of these array assignments had to be done completely before the next one was done, which really caused a problem for parallelization. So Fortran added do concurrent, which replaces for all. In fact, for all is now deprecated, obsolescent. And do concurrent doesn't cause parallelization. What it does is it makes certain assumptions, such as you don't have cross iteration dependencies, that allow for parallelization, and actually many compilers do parallelize a do concurrent if you've asked for automatic parallelization. Intel Fortran, for example, will do this. But even without parallelization, things like OpenMP type parallelization, it can help with instruction level parallelization, vectorization, because it gives the compiler information that allows it to optimize better. A do concurrent has a concurrent header. It used to be called a for all header, but now for all is going away. So, and it looks sort of like a regular do loop, except that instead of the index where you say 1, 10 as an example, that implies a sequence, you have essentially a range of values that the control variable can take, and an optional mask expression that restricts the combinations. So in this example here I have at the bottom, we have two index variables, I and j, that can have the values from 1 to 10, so that's 100 possible combinations, but the iterations will execute only if the a sub I is greater than 0 and b sub j is less than 1. I guess that my screen is being cut off by the pictures of the people here. So that's a mask, and that's optional. And again, you can have a step, so it doesn't have to be a strict sequence. The compiler will decide what all of the possible combinations and all the allowed combinations are at the beginning of the do concurrent, and then will do the iterations in any order and to any degree of parallelization. So an implementation could just do it all sequentially, but it could do them in random orders, or it can do them in parallel. Fortran 2018 extended do concurrent to add locality specifications, which, if you're familiar with OpenMP and this looks familiar, you're right, because it was borrowed directly from OpenMP. There were concerns that the way the original specification was, the compiler was forced to try to figure out if variables that were created used inside each iteration were local to a particular iteration, or if it needed to worry about references across iterations. So you can specify that something is local. Local is that this is local to this routine, this iteration only, and is undefined at the beginning of the iteration. Local init says that it's local to this iteration, but it takes its value from the same named variable that existed outside the do concurrent. Shared means that this variable is shared across all the iterations. And there's also a default none, which tells the compiler that the user is required to specify the locality of every variable that's used in the do concurrent. Here is an example with the locality specification. So outside the do concurrent, we've declared a couple of allocatable arrays, A and B. I see I have a syntax error here. That should be A parenthesis colon parenthesis. How did I miss that? I'm sure I took this example from this book, Modern Fortran Explained, by Mike Metcalf, John Reed, and Malcolm Cohen. Excellent book, explaining lots of things in the standard. And I'm sure they didn't make this mistake. I did when I typed it in. Okay, so these are A and B are allocatable arrays that we've allocated somewhere, and then we have a variable X, scalar X. So they have a do concurrent, and I can go from 1 to whatever the size of A is. X is local, A and B are shared, and it does its thing, and it can be done in any order and to any degree of parallelization. Okay, now we get to the fun things for parallelization. Now, do concurrent is essentially your local system, shared memory, and all of that, but coarrays can go much bigger. Coarrays started a long time ago, back in the late 1990s, I think. Where Cray had the initial implementation on their Cray architecture systems. It's single program, multiple data. And what this means is that you write one program that is replicated multiple times, and each instance of that program is called an image, and it could be on the same system, it could be on a cluster, it could be thousands of them. The data coarrays are shared across, they're distributed across the different images. So pieces of a coarray exist on each image. Each image has its own local version part of the coarray. When you start a coarray application, there is a fixed number of images that is determined by some method outside of the program. Each image has got its own set of variables. It's a program, and it just has its own ordinary variables, but it also has coarrays that have co-subscripts that are specified in square brackets if you want to access the version of that variable that occurs on another image. Images, they execute mostly asynchronously, but there are various synchronization constructs, and there is an order of execution. And there are various intrinsics for dealing with it. Okay, I have a question. Okay, disregarding the last line in my do concurrent example, would including the if a paren I greater than 0 as scalar mask result in different performance? I really can't answer that sort of question about whether a particular coding style would exist in create different performance. This is the sort of thing you just have to try it. I would guess that especially if the do concurrent block did a lot of things, that reducing the number of iterations that were actually executed could be a better performing choice than doing them all and doing a test within it. But that all depends on how your particular compiler does its executes the mask, implements the mask. So I really couldn't say. But the thing with all of these sorts of things is try the performance one way. If you have acceptable performance, always write things that's clear to the programmer. I've always said that I hate writing programs where I am constantly worrying about, is this statement faster than that statement? Start out by writing the program that clearly specifies what you want to do so that you understand it and maybe the compiler can understand it. Test its performance. If its performance is not adequate, use a performance profiler to see where the time is being spent. Most cases you will find that the time is being spent in places you did not expect. So don't spend a lot of time trying to optimize in advance. Do be aware of things that are generally problematic. Fortran is a column major order language. So, accessing arrays in the correct memory order, things like that, that you need to pay attention to. But whether you do the mask or you do a test within the do concurrent block, I really couldn't comment as to which one is going to be faster. And it may depend on the implementation. So here's an example of coarray syntax. You can have a coarray that's a scalar, which is a little bit weird, noting that you always have asterisk as the last upper co-bound, and this gets filled in at runtime with the number of images you have. So if we were on, if we had a coarray program that had 4 images, in this case, there would be R of 1, 2, 3, 4. And again, just like you can with regular arrays, you can specify a different lower bound, and then the extent will be the number of images you have. The second line here declares an actual array that has parts on multiple images. Note the save attribute. Save attribute means that this variable remains defined across routine boundaries. There are, the language requires you to declare procedure local variables as save if they're going to be coarrays. If they're not going to be allocatable, you can generally coarrays are allocatable, but they don't have to be. So then there's a couple of local variables. These are not coarrays. You can assign to a local variable from a coarray, or you can assign to a coarray variable from a local variable. Okay, here's an interesting, the x paren colon paren equals. This, well, this probably doesn't matter so much. I don't like using paren colon paren on the left side of assignment statements. And actually, I have a Dr. Fortran article where I talk about that. If this were an allocatable array, it could change the meaning of what it's doing. An interesting thing about if you have a coarray and you reference it without the co-subscript, that's the thing in the square brackets, then that's your local version. It's the equivalent of using the this image intrinsic in your co-subscript. And I have a question. Let's see. No, that was just a comment. Okay. So I don't see this. Okay. If you have a, most coarray implementations, they have a shared memory model available. So each image is one, they're separate programs running. And in fact, many of the implementations use MPI. to implement coarrays. Intel certainly does. You can have multiple images executing on a node. You can mix coarrays and OpenMP. I've seen people do that. There are various implementations possible. I know that Fortran with its open coarrays library, which is licensed separately. I haven't quite figured out how all that works, but it's not bundled with Fortran, or at least it didn't used to be. They have different ways of doing the memory sharing. I borrowed these slides, some of these slides from John Reed. He and I find different things important. John was one of the original authors of the coarray specification, so he sometimes gets very deep in the details of implementation. But you really shouldn't worry too much about implementation. It's just supposedly work. Okay, so we have a question from Merrick. So x paren colon paren equals x paren colon paren square bracket p would be interprocessor communication. Yes. It would fetch the value of the X array that exists on image P, assuming image P is not the current image, and then it'll assign it to the local image's version of X. Images, they start off, well, first of all, they all wait at the beginning for all of them to start. And then there are, they operate on their own, except when there are synchronization points. Not all of the synchronization points are explicit, some are not. Sync all is what we call the big hammer approach, which means everybody waits at the sync all statement until every image has executed the same number of this same sync all statement. You can say, wait for this set of images, where image set is an array of image index numbers, and images are numbered 1 to n. There is a critical section available. And these are image control statements. Also, if you do allocate, allocate and deallocate are implicitly image synchronization points. Coarray execution is done in the concept of image segments, where all images run certain segments up until a synchronization point, and then another segment starts. So in this example, everybody runs up to the sync all. And now if we're on image 1, image 1 does this next part where it does the read, and then it does another sync all, and that ends segment 2, and now segment 3 starts, and the other images can continue on at segment 3. So the other images wait until wait on that second sync all until image 1 finishes doing the read part. So there is as it says here, there's a partial ordering of the segments. Otherwise, each image can continue on its own. You are required to make sure that if a variable changes on one image in a segment, you can't reference it or have it become undefined in another segment unless the segments are in the proper synchronization. So it's up to you to do this. You can have allocatable coarrays. You can have a pointer to a coarray, but you can't allocate it that way. You have to use allocatable coarrays. And here we have, this is deferred shape, and it's deferred co-shape. And you can have not just a single co-rank, but you can have multiple co-ranks. Now remember earlier, I said that the maximum array dimension was 15. Well, that's not quite true. It's 15, the maximum rank of 15 minus the co-rank. So you can have a co-rank of 15 as long as it's a scalar, or you can have 7 and 8, etc. And here we allocate an array with, again, the upper bound of asterisk, because we don't know how many images there are. You have to make sure that every image allocates a coarray the same way. And as I mentioned earlier, all images synchronize at an allocate or deallocate. So everybody is doing it at the same time and is consistent. You can have a procedure with a dummy argument that's a coarray, and it can be explicit shape, it can be assumed size, it can be assumed shape, and can be allocatable. There are things you can't do with coarrays, so there's never a copy in, copy out, and this is another case where an explicit interface is absolutely required, because otherwise the calling procedure doesn't know how to pass the information. You can have a coarray that is itself a derived type. And it can have allocatable or pointer components, but you can't allocate or you can't reference a pointer to coarray on another image or allocate a coarray on another image. Okay, so Thomas asks, how could one picture having higher coarray rank? I'll actually have an example of this later, so we'll get to that in a moment. I agree that it's a little confusing, but there's a possible reason. In Fortran 2008, coarray images were uniformly numbered, starting at 1, depending on whatever your environment had. And Fortran 2018 added a feature called teams, where you could split the sequence of coarrays into the sequence of images into groups that operated in particular ways. And there's also, notice I have these spare images. There is also now the capability of recognizing when an image has failed. So if you have a really, really big cluster, and I'm sure some of you folks do use really, really big clusters with hundreds or thousands of nodes, you can have a coarray with hundreds and thousands of images. Chances are one of those might not get all the way through the program. And the more images you have, the greater the chance is that, that something's going to fail. So Fortran 2018 also added the concept of failed images and the ability to detect and recover from an image failing. Now, I'll talk about this in a little bit. Going back to the earlier question about multi-dimensional co-arrays. I thought I had an example of this. I don't really. I'm not sure I can really come up with a good example of why you would want a co-rank of more than one, but I have seen examples where that made sense. Perhaps you are dividing a problem into a two-dimensional or three-dimensional space, and you want to look at, let's say you have halo cells, and you want to reference your neighbor, and so that's where a two-dimensional grid or a three-dimensional cube might make sense. Made sense. I'm amazed. Okay. A big problem with the original co-arrays is that essentially you had a monolithic program that knew what the indexes of all of the images were, what all the co-subscripts were. And that meant you couldn't write a library that used co-arrays to be independent of what it was being used for. And as I had the little example with a weather modeling program that had land and sky and sea. So Teams allows you to group co-array images into collections where they operate independently, and they have their own uniform image numbers, starting with 1 for the first image in the team, etc. Any program that runs on a whole machine, it should also be able to run on a team. There are collective routines, which I talk about a little bit, but you want to be able to say, I want to synchronize only with my team, or I want to allocate things only with my team, because another team might be doing things very, very differently. So what was added was a special derived type called team type, and this is declared in the intrinsic module ISO Fortran ENV. If you declare a scalar object of this type, it has to be a co-array, that means it's a team of images. And now there's a new form team statement that creates a team you specify the team object. I actually have an example of this. So images with the same value of number. Oh yes, the number, that's sort of like a code that you supply, that you create for which team it is. And then new team is the team variable. All images from and that team then synchronize. And then there's change team. So once you've created the team, you now have an image that essentially says, okay, now I'm going to join this team. And it declares a local name for a co-array that exists outside of the change team block. And once inside the change team, it's now part of that team named by the team variable. And it does whatever it needs to do independent of the other teams. All of the teams will synchronize at the change team and then the end team statement. This is going to be a very expensive operation, so you shouldn't do it a lot. You can access things from another team by referencing their, how does this work? Yes. change team. You can do a sync team and reference a team with a team variable. Excuse me. So you can now do a reference based on a team variable. There are collectives where you do an operation that is spread across all of the images of your team. Co-broadcast sends data to all of the images of your team. You don't have to use teams, of course. You can just do it the old way without with everybody is running the same, all of the images together. There's max and min and sum. Again, you take an array and it distributes that work to the various images, and they collect the information and then return the result to either the caller or to a specified image. And then there's also co-reduce, which is interesting, where you supply your own function. Can be anything you want, and all of the images in your team will execute that reduce function and collect the result and send it to whatever the desired team is. Here's an example with co-reduce, and we're going to make our own version of the all intrinsic that that essentially ands all of the elements together and returns true if every element is true, otherwise it returns false. So we have a function that we call both that returns a scalar value. We call co-reduce, pass it let's get this right. Okay. Pass it the thing that comes in, the scalar value in. Somehow I don't think I did this right. I think that should be, what did I do here? Yeah. Now I'm a little bit confused here. There really should be an array. And it will call the both function across the various images, return the result to the caller. I apologize that I got this wrong. Spent so much time on these slides. Another feature added. Let me just see. Another feature added in Fortran 2018 are events. Event is a lightweight synchronization feature that allows you to wait until some operation has happened on another image or has happened a number of times. You might, for example, implement a semaphore that way, or you might want to wait till 10 images have done something before you continue. An event variable is a scalar coarray of type event type. This is again another special type. And if you're familiar with semaphores, it works pretty much like that. When you do an event post, it increments the count. When you do a wait, it decrements the count. And you can say wait until a particular count. Yeah, okay. This example doesn't show the count, but you can specify optionally the count. Here's a larger example. It's an outline. It's not a complete program, but we set up a tree structure across all of the various coarrays. And now we loop through the our part of the tree, but we want to wait until the child nodes have completed. So here we have the until count specified. And now once all of the children are complete, now we've got all of the children done, and we can get back, get the result. Okay, I have a question. Do I think MPI could be replaced by using coarrays? And do you think it is worth looking into this direction for existing code? Yes, in many cases, you can, an MPI application is a good choice for considering coarrays. I'll comment that many, again, that many coarray implementations use MPI underneath. They don't necessarily all, but the concepts are somewhat similar. With MPI, though, you are explicitly passing and receiving information, and the Fortran compiler doesn't understand what you're doing. I mean, there are some hints. You can say it's asynchronous, but it doesn't know what an MPI send or an MPI receive is doing. With coarrays, it's built into the language. There are built-in synchronization points, and less worry about needing to do type, type neutral things, because you're sending just arbitrary sets of data. You can use coarray variables in many, in pretty much any place that you could use an ordinary Fortran variable. I mentioned earlier that Fortran 2018 added the concept of failing images. So now you can detect, you can ask, are there images that are known to be failed? And known failure is perhaps not quite as robust as you might like. It means that something happened, but the runtime system was able to detect that the program failed, and in particular, if a image executed a stop statement, that would certainly be a failure. There are some kinds of failure. If it got a seg fault, okay, that would probably not be recognizable. But there is a way sort of knowing that an image is not responding. If you detect that there are a failed image, you can reallocate certain images to another team or can continue processing. So here's an example where we did a get team, we did a change team, and then we just sync all in our team. And we're looking to see whether maybe some of the team members dropped out because they failed somehow. So if the stat is stat failed image, then which is a defined constant in intrinsic module ISO Fortran env for environment, then we exit the change team. And now we can detect that something failed, and then we do whatever it is to deal with the failure. We might be either print a message, or it might be recruit one of the reserve images to join the team and have it continue with the execution. You can even detect in a remote reference that an image has failed. So if I ask for the value of B on image 3, and image 3 has failed, the status will come back with stat failed image, and I can deal with that. Right, somebody asked earlier about replacing MPI with coarrays. Again, references to the local data are obvious to the user, to the reader, and to the compiler. You might be able to hear my cat saying, "I want in." She can't help. It's easier to maintain code. It's Fortran code. It's not a series of MPI calls. So you have type checking. You have your normal Fortran type conversion. The compiler can optimize its communication based on the semantics of coarrays. Certainly can do all of its local optimizations, and the compiler doesn't have to keep track of a lot of things that it might otherwise, or the user doesn't have to keep track of a lot of things that they might otherwise. It is possible to use coarray to the existing, to add coarrays to the existing MPI code. I've seen people do that. It gets a little bit tricky. The problem is that, especially if MPI is the underlying mechanism, when your coarray program starts, it's going to do its own MPI run and try to use all of the coarray images for that. So I'm not sure how that would work. It might be difficult. I will admit, and it may be already obvious, coarrays are not the thing I'm the strongest on. There are some parts of the language I understand better than others, but I've tried to understand as much about coarrays as I can. There's certainly lots more information available, and I'd be glad to make references to further documentation if you need it. So here's a coarray program that I wrote. It's actually an example that I wrote for the Intel implementation, and it calculates an approximation of pi using a Monte Carlo technique. Basically, it's generate random numbers from 0 to 1, two random numbers, and that you're throwing a dart at a quarter of a dartboard and seeing whether the dart falls within the circle or outside the circle. And so here I had to declare some kind constants. This is the way that you should declare kind constants. So I have big int is an integer kind that can handle at least 15 decimal digits, and k double is a real kind that can handle 15 digits and a range of 10 to the 300. I declare the number of trials, really big number here. I have a value of pi that's for comparison, and I have a coarray that is actually it's a scalar coarray, but each image has its own copy of it. Now, image 1 starts out, checks to make sure the number of images is divisible by the number of trials is divisible by the number of images. And then each image calls random number. Random init, by the way, is a new Fortran 2018 intrinsic that initializes the random number generator to, and you can say whether I want it to be repeatable. In other words, every time I run this program, do I get a different sequence of random numbers? And image distinct is, does every image in this coarray application have its own sequence of random numbers, or do they all share the same sequence? And when we were developing this, there were, some people wanted it to do one way, some people wanted it to do the other way. And so we added these arguments to random init to specify what you wanted. And within each image for the number of trials for our part of the trials. We call random number X and Y. And note I use a semicolon here to divide them so you can have two statements in the same line. And I say, if the radius is within the circle, then we add 1 to the total. And just add at the end a little print after the end of the loop to say how many values we found that were within the circle. Now, remember, this is within a quarter of the circle. So we wait for everybody to finish. And then image 1 does the summing. So it sums all of the totals across all the images. And now I compute pi by dividing the total by the number of trials and multiplying it by 4. And I have to convert all of these things to double precision from the integer type. And now I print the computed value and the relative error based on the actual value of pi and give a timing. And here's an example I ran on my system. So notice that every image, first of all, they complete in different orders, and they found different numbers of values within the quarter circle. And now we computed the value of pi, and you can see this is a really terrible way of estimating the value of pi, because even with lots and lots and lots of trials, the error is pretty bad. But it's an interesting demonstration of coarrays. So I ran this on a 6-core processor with 12 threads across 6 cores. Okay, now I'm done talking about coarrays. Are there any questions about coarrays? Okay, see, we have got about half an hour left. All right, I'll try to, well, we're working out. The timing will be right. I'm going to talk a little bit about the future of Fortran, because Fortran never sleeps. And we are well underway of defining the next revision of the Fortran standard. It's not going to be a big one like Fortran 2018 was. But it will have some features that are popular. In fact, we did a survey. I ran a survey in 2017, 2018, ran for 6 months, publicized it widely, asking for users to suggest what they would like to see in the next version of Fortran. And we got hundreds of responses, and I compiled them all into this WG5 document, which you can find on the WG5 website. I have a link to that later in the presentation. And our goal is to have it published no later than 2023. The pandemic caused us some problems. We had to cancel our 2020 WG5 meeting. And so far we've held virtual meetings. So yeah, 2 virtual meetings for the J3 US committee. We are going to have a virtual meeting for WG5 in June, but we're getting close to getting finished. But there's a lot of work left to be done. And after we finish 202X, the next one we're calling 202Y, and I call it that because I want to say that this is going to happen in just another few years. It's not going to be 8-10 years the way it was between Fortran 2010 and 2018. Right? Between Fortran 2008 and 2018, Fortran 2008 was published in 2010. So here are the features that are going to be, are planned to be in Fortran 202X, which we'll call 2023 if it happens to be published in 2023. If you go to the J3 website, j3-fortran.org, you can look at paper numbers, the papers, and I have the references to the papers here. And these are some of the features that we've already got done in development. And in fact, there is actually a draft of the next of 202X document that's paper 21-007 R1. I think it's R1. You can look at that and see these things defined so far. So optional argument to CF pointer. CF pointer casts a C pointer to a Fortran pointer, and previously you couldn't specify lower bounds, you could only specify an extent for an array. So now you would be able to specify lower bounds. I mentioned earlier that about source line length and statement length was changing, and it's going to be changing to basically 1 million characters in your source line with no specific length of each individual line. Compilers are required to report any characters after any line length limit if they have one. I believe there's a 10,000 minimum line length limit. Adding some trig functions that have been popularly implemented already, degree routines, also some trig functions scaled by pi, adding a selected logical kind intrinsic to go along with selected int kind for integers, selected real kind for reals. And there are these constants in the ISO Fortran ENV intrinsic module that can be used for declaring various variables of particular kinds. I don't like using those. I talk about that in my It Takes All Kinds Dr. Fortran article, but they're there. There had been in Fortran 2003 a optional part of the standard for varying length strings, actually for Fortran 90. And we got rid of it in Fortran 2008 because nobody had implemented it. And with deferred length allocatable characters, that does almost everything that this variable length string package had done. But there were a couple of functions that were missing, and we've added a split function for sort of parsing a string based on separators. And there's some disagreement with the implementation that we've specified so far. So this might change between now and the time that the standard gets ratified. When I was talking about C interoperability, I said you could pass a arbitrary length, excuse me, Fortran string to a C routine where the array was declared as an array of single characters. That's nice, but there was no corresponding thing in the other direction for having a C program call Fortran, passing it a null terminated string and turning that into something that could be used as a Fortran string. So that's what CF stir pointer does. It takes a C string, which is an array of bytes, and turns it into a pointer to a character string of the correct length. And FC string just goes the other way of helping you tack a null character to the end of a string. There is the AT format for trimming strings, so you don't have to use trim in your IO list anymore. Something that people have been asking for a very, very long time is that the F format in formatted IO for reals, it was implementation dependent whether a value less than 1 had a leading 0 printed or not. And some implementations put the leading 0 and some did not. So now there will be a format that allows you to control that. It's also controllable in the open statement. Will now be able to have arrays of derived type with co-array components. You can't have that in Fortran 2018. A new co-array feature, put with notify, where you send the information to another image and then get notified when that has been received. Now that we have deferred length character allocatables, There are other places you would like to use it. We had initially wanted to do something like being able to read into a deferred length allocatable character and have the length set automatically, but we found that that just didn't work right. It was incompatible with existing code. So now that's restricted to internal write, but also all of the statements and functions that take IO message or error message can take an allocatable deferred length character, and they will be allocated to the necessary length. Do concurrent will add a reduction specifier. We have binary constants in more places. I have a Dr. Fortran article on that. I did that last August, I think. Some more, let's see, what do we get? We're trying to get into generic programming. We wanted to do really full generic programming in Fortran 202X, but we couldn't agree on the approach at that time. So what we did was we said, all right, we're going to start work now on generic programming, and there's a generic subgroup that's been actively working on that. And we added a couple of things that we thought would be useful for generic programming, type of and class of. So when you're declaring a dummy argument, rather than having to know what the type of an argument is, you can declare it using the type of some other argument or the class of some other argument. And similarly with bounds and rank, you can declare an argument that's based on the bounds and rank of some other another dummy argument. And there's some rank agnostic things to, again, help with generic programming. But again, there's some disagreement about the decisions that were made there. So this may change between now and the time that the standard is formalized. We have some features that WG5 has asked for, but they haven't been fully specified yet. Protected components. This is a component of a derived type that is visible when you from a module that you've used, but you're not allowed to change it. Typed enumerators. Fortran does have what we call enumerators. They're really just another way of declaring named constants, parameter constants. Not as useful as the way C does it, where C or C++, where an enumerator set has a type and you can restrict a variable or a dummy argument to be enumerators of those type. Conditional expressions, that's probably not going to happen. It's like the question mark operator in C. Short circuit logical operators, again, that's likely not going to happen. These will probably get removed from the work list. And here's one that's been troubling us for a while. What does intent mean on a pointer? Currently, it means that the value, that the pointer itself cannot be redefined. So you can't reallocate the pointer, but it doesn't say that you can't change the target. So we want a variant of intent that applies to the pointer target. So here are some links for additional information. There's the WG5 website, which is where the international documents are. You won't find the Fortran standard here because ISO doesn't allow us to have a copy of their copyrighted document on the web. So we don't have that there, but we have a lot of other documents. Then there's the J3 website. That is where all the papers go. And there is a document that is our reference document for Fortran 2018. It is the same text as the standard document, but it has line numbers and it has other things that the committee uses for interpretations and for edits towards the next version. And 21-007 is the current draft for Fortran 202X. There's my blog. I've mentioned it multiple times. I don't get doing advertising on the blog, so I don't get any money if you go visit my blog. It's there just for information. no marketing there. There is a GitHub discussion forum that Andrei Ksertik created for discussions for future Fortran proposals, and that's a great place to look at, propose and discuss ideas for future Fortran standards. There is a website, a Fortran discourse, which for just general Fortran language questions. So lots of people, including myself, participate there and help explain Fortran things to people with questions. There's lots of knowledgeable people who answer questions there. Okay, so now we are, I'm done with my slides. Okay, timing didn't work out too bad. It's we have 24 minutes left. And so any general questions about Fortran, I'm going to stop sharing, and you know, you can raise your hand and I'll call on you, or you can type things in the by the way, the raise hand is under the reactions button if you aren't familiar with that. And okay, so Paul asks, when do you recommend to use selected int kind versus int3264 from ISO Fortran N? All the time. If you, the problem I have with the int32, int64 constants is that all they tell you is the number of bits in that particular kind's storage representation. They don't tell you anything about it. And this is maybe not so much a problem with integers as it is with reals, because you don't know, for example, if you say, well, okay, I want a something with 20 decimal digits. You know, is there a quad, what we would call a quad precision type? Well, you know, maybe there's a real 128 there that's 128 bits, but it doesn't have the number of precision bits that you want. It might not have the range you want. And I used to work on the system where there were 3 different double precision floating point formats, only one of which was IEEE. There is IEEE selected real kind if you want specifically IEEE semantics. In fact, there are 3 IEEE modules that I didn't talk about here that if you want specific IEEE things like denormals and things like, and nans, you can use that to manipulate and get those. The int32, int64, they're shortcuts. I don't like them because they don't tell me really what I want to know. If you want something that's interoperable with a structure in another language, use the kind values in ISO C binding. You know, I'm not going to complain a lot if you use int32, int64, real 64, but I think it's lazy. And I'd rather use the selected intrinsics to do that. Any other questions, comments, and not just about what I talked about here, but anything with Fortran? I'll take any questions. Okay. If we aim to OpenMP parallelize a parent's class routine, how do we tell OpenMP that the child class member variables need to be private? I'm going to be the first to admit that I am not an OpenMP expert. I assume you mean thread private rather than what Fortran calls private. At least that's my assumption.
Yes, talking about OMP private. Sorry.
Oh yeah, you're talking about OMP private. Well, I mean, any variable, local variable that you declare is, you know, you can say it's thread private, and it's just a variable. And even if it's a trying to parallelize a class routine, and a class is I don't know how to answer that. You know, I just based on my superficial knowledge of OpenMP, I don't know that there's an issue there, but there might be. But that would be a good question to ask in the Fortran discourse, because there are people who know OpenMP very well, and they know the Fortran polymorphism stuff, the object-oriented stuff very well, and could probably do a better job answering that than I could. And I don't know everything.
Sure, that's perfectly fine. I was also asking this question on behalf of a colleague who can't be here today. So I will just tell him what you told us.
Yeah, I mean, I've never used OpenMP in an actual application, so I'm not a good person to ask that question. Okay, so Fabian asks, are there any well-known pitfalls with respect to performance when applying OOP concepts? Okay, the standard thing with any new feature in the language is that compilers try to get it right first and then get it fast later. And this was certainly a case with array operations when Fortran 90 came out. But over time, compilers did it better. Most of the OOP stuff is compile time known. There are things such as parameterized derived types that that are some of those where length parameters are runtime, and some compilers have more of a problem with that than others. I would say that the one pitfall I know of, okay, here's one that is really a big one, at least in the implementations I'm aware of. Let's say that you've written a routine that takes a dummy argument that you've declared as class something. That so it can it can accept arguments of the parent class and any parent type and any of the extensions up to the declared or any of the extensions. You then call it passing something that's declared as type something. Let's say type parent class or one of the type class extensions. The compiler has to construct the data structure that the called routine will use to identify what the dynamic type is, because that information doesn't exist with just something that's just declared as a type. There are optimal ways of doing that. There are non-optimal ways of doing that. The Intel compiler pretty much does the non-optimal way of in that it constructs this big data structure on the stack every time you call. And that takes a lot of instructions. So what you might consider doing in such a case is you might declare, let's say, a pointer that's of a class and pass that, because now the information is created once and then doesn't have to be created on every call. And there are other compilers that might do it entirely differently and that don't have performance implication. So again, as I suggested earlier, write it the clear way, the way that you understand it. If the performance is not adequate, run a performance analyzer and see where the time is being taken. And if you see that 80% of your time is being taken on a call, on the actual call to some routine that does one of these things, passes a type to a class, then you say, okay, well, let's see if I can find a way to make that faster. That's the one big OOP performance killer that I'm aware of. Template programming. Okay, what is the recommended way of template programming? This is actively under development in the standards committee. Templates and generics go together, and there are several proposals for how to do this. Definitely go to that GitHub site that I linked earlier. These slides will be available. I can send Norbert my slide deck and he can make that available to, so you'll have all those links. And of course, the video of this I know is going to be available at some point. But yes, we will have templates in the future Fortran standard. Right now, the way people are doing it is very clumsily with preprocessors. There are people who are doing it. There are people in the doing this discussion who are familiar with what's going on, and I recommend that you go look there and see what's happening. Anybody else? What is the difference between stream and direct IO? Direct IO, already uses a raw stream of bytes. Okay. Well, first of all, direct IO is fixed record length. So, I mean, yeah, you could declare something that's direct access single byte record, but you can't, and which is the way a lot of people were doing it before. This is stream IO is something that's closer to C, where you can write variable numbers of bytes as in a single IO statement. With direct IO, you can only write one record at a time, 1 byte at a time, read 1 byte at a time. And with stream, you can have both formatted and unformatted. With stream IO, there are no record lengths the way there are in sequential unformatted records, and those record lengths are implementation defined. With stream IO, it's just raw bytes. And it's also good for interoperating with files read or written by C. By C, yes, C. Okay, next. Okay, Marek, I see your hand is up. You can unmute and
first I clapped, then I raised the hand. Sorry. So I have a question about your opinion of HPF-like languages. So you said HPF did not go anywhere, and I did not ever use HPF, but I used 2 languages that were similar. So Connection Machine Fortran and the Cray Fortran. Cray Fortran was extremely inefficient. Nobody liked it, but I very much liked Connection Machine Fortran. It was easy. It was very efficient in those days. Do you see that something like this is going to come again, or is Co-array Fortran basically playing this role now? Will there be any more parallel Fortran-like language?
let's see. Okay, I'm not familiar with Connection Machines Fortran. Certainly back in the 1980s, and I guess yeah, 70s and 80s, there were lots of these massively parallel hardware designs, all of them unique, and each hardware vendor then had to write compilers and design languages that took advantage of their implementation. And Cray did this too. And I'm not quite sure what you meant about Cray Fortran. I mean, I know that Cray had a very good implementation of Fortran for their systems.
They had a Cray parallel Fortran. I think it was called Craft. Okay,
I'm not familiar with that, but I don't think that there are going to be additional parallel language feature, different parallel language features. Co-arrays is where Fortran is headed, and we're looking to make co-arrays even more useful. There are fewer of these unusual design hardware systems out there. Clusters has pretty much taken over that. I'm amused because I work for DEC, and we had VAX clusters, the first implementation of this sort of thing. And then the rest of the world picked that up later. But no, I don't see Fortran adding yet another parallel language concept. I think coarrays is it. And we're going to spend our time looking at ways to make coarrays more useful. And certainly Cray's experience with coarrays over the last 10, 12 years has shown it to work well for them. And the community is picking up on that, and lots of people are using coarrays. Okay, so Norbert asks, performance of codes depends on interaction between compiler and CPU platform. Do I know if Intel is still investing in Fortran compilers? Oh, I do know that, and yes, absolutely they are. You might be aware that Intel is transitioning their code generator and optimizer from their own proprietary one to LLVM. The IFX compiler that's currently available in their one API tool set uses LLVM. It is not a complete Fortran compiler at this time. It's a beta. It doesn't support a lot of things, but yes, there is a large team at Fortran at Intel. I know pretty much everybody on that team, and they are absolutely investing. They're other hardware vendors. I know AMD has got a Fortran team going. NVIDIA has a Fortran team going. So there's lots of development of Fortran compilers going on. Even though there have been some consolidation in the industry, there are, every high performance computing hardware vendor knows they need a Fortran to compete. So that's where it's going. Okay, discussion. Oh yeah, some hardware is moving to ARM. How do I see ARM as a Fortran platform? It's just another architecture. I don't see any difference. I know that there are, NVIDIA is doing a Fortran for ARM, and the fact that most of these compilers are using LLVM as their common backend means that ARM is naturally going to be a target for Fortran compilers. So I expect to see a lot more of that. Not every vendor is going to go there. I don't expect Intel to do an ARM compiler, for example, but there will be Fortran compilers for ARM. There already are, really. But ARM is moving into the server world, so yeah, absolutely. There needs to be Fortran in that world. Discussion include concepts aimed at GPUs into the standard along the lines of CUDA Fortran. Okay. The answer to that is not in the standard, and here's my take on it. All right, I've been around for a long time in the Fortran world. Okay, so it's going on 40 plus years now. And I have seen accelerators of various kinds come and go. And what happens is that for a while, the CPU can't keep up, can't do floating point stuff fast enough. So there's some sort of card that you add on that does floating point really, really fast. And then compilers are written to with extensions to take advantage of those. Back when I worked at DEC, we had VAX vectors, and we had a separate vector processor on the VAXs. There was floating point systems that had an accelerator that plugged into various systems. And then the CPUs sort of catch up. And the need for these accelerators goes away. I view the current GPU thing as another one of these short-term fads. And you're already seeing vendors take the architectures they build for GPUs and adapting them into their base computing system. Intel has been doing this. They sort of made a little bit of a false start with the it had been called the Larrabee project, the Xeon Phi, but now they have they're doing these massive core processors. They've talked about, there's something codenamed Ponte Vecchio or something like that. I'm not privy to what Intel is doing internally. I only know what I read about in the news, but I expect that over the next 5 to 10 years that these add-on accelerators are going to disappear and no longer be useful. And our approach on the Fortran standard is we are looking for the long term. So we don't want to add features to the standard that assume a particular hardware implementation. Somebody was proposing a fast mem attribute a little while ago, and we said eventually all memory is going to be fast memory, so there's really no point to that. And what we do see is these hardware vendors using OpenMP, OpenACC. NVIDIA's got CUDA Fortran, but I think that's going to sort of fall by the wayside. And both OpenMP and OpenACC have GPU accelerator syntax, and the compilers from those various vendors, including Intel, target those accelerators. We would rather see that sort of stuff happen as directive-based programming rather than build it into the Fortran language, where we need to, one, get it right for everybody, for all possible future architectures, for all time. And that means nothing's going to be acceptable to anybody. And let the hardware people work faster with the directive-based things. Okay. How do I compare old HPC languages to modern Julia Rust? I can't do that because I have not studied some of these modern languages. I know they're very popular. They can be very good for some things. I am not a language bigot. I don't believe that one language is absolutely right for everything. Use the language that works best for you. Fortran is good for some things. Some of these other languages may be good for other things. You can mix the languages. Let's make sure I don't miss something. Okay, is there any way to ignore some specific type of warnings and treat other types of warnings and errors at the same time? You'd have to look to your compiler's documentation for that. I know that the Intel compiler has a way to do that. I'm sure other compilers do also, and you might not be able to disable all kinds of warnings. You might not be able to turn all kinds of errors into warnings or warnings into errors. But some compilers do have that feature. There's nothing in the Fortran standard about that. But I would argue that if the compiler is giving you warnings or errors, you are better off figuring out how to rewrite your code to not get those warnings or errors rather than telling the compiler to ignore them. Okay, Marek asks, we have not yet added OpenMP to our MPI code. Does it make sense to focus on Fortran features like do concurrent or OpenMP for hybrid parallelization? The do concurrent is great, but first of all, you'd have to ask the compiler to automatically parallelize, and so it would parallelize all loops. OpenMP gives you much finer control than the Fortran syntax does. So we're adding to Fortran, as you've seen during my talk, but I think if you are familiar with OpenMP and are comfortable with it, that I would go that way. Do worry about oversubscribing your processors because OpenMP and coarrays or MPI, they don't talk to each other, so they don't know that how many processors you have available. So you'll need to worry about that. Okay, it's now 3:30 your time or 6:30 your time. I can take more questions, or we can end it now, and you can send me email if you have further questions.
Are there further questions at all?
No.
Then I think I can thank you. It was a very interesting and intensive course. So what we have seen is that you get less questions or only few questions to core arrays. But I can tell you is that there's a lot of discussion happening inside the chat. So in some other chats. So people are very interesting to follow your, let us say, guidelines or your following these new impressions. So thank you, Steve, for taking your time to introduce us to all these new features to show us the future of Fortran. I think some of us are more motivated now to continue with Fortran. And
good. I'm glad to hear it.
And it might be the case that you will get additional questions in the future from our group or from Aachen.
Yeah, I welcome questions.
So yeah, thank you again, and I wish you a nice day, and to all the others a nice evening.
Okay, thank you. This has been great. I enjoyed it very much.
And I've seen that you have been in Cologne in the past, so I saw some.
Yes, I have been to Cologne. Well, my father was born in Leipzig.
Oh, okay.
And I've visited Germany several times, so on vacation and also at Fortran standards meetings. But yes, I've been to Cologne, and actually I'll be back there. I've vacationed in various places in Germany a couple of times, taking cruises along the rivers.
So Aachen is close by to Cologne, so it is around between 40 and 50 kilometers. So it is a trip worth. So let us know if you come to Aachen, then we can invite you and show you our codes maybe.
Okay, I will do that.
And we can show you around, of course.
Yes. Okay, very good.
Maybe less experts.
Okay. Goodbye, everybody.
From my side also. Thank you, Steve. Thank you very much.